In this video we're going to examine stationing. Stationing serves as the backbone to all engineering projects. It gives you a reference to all points that need to be staked, so any improvements is going to be referenced to this baseline, to this center line, and it's going to be referenced as a station and offset from that baseline. So you can see we start here. Our first station is 0 plus 0, 0, and our full stations are written as 1 plus 0, 0, 2 plus 0, 0. What that means is that from 0 plus 0, 0 to 1 plus 0, 0 is 100 feet. So each of these is even 100-foot stations. So from 2 plus 0, 0 to 3 plus 0, 0 is an even 100-foot station. The distance, or as you're standing on the baseline looking up station, so as the stations are increasing, anything that is to the right of that baseline is going to have a right offset. Anything that's to the left of that baseline is going to have a left offset. So again, as you're looking up station, the stations are increasing. As you're looking down station, the stations are decreasing in numbers. So if you want to reference a point that's out here and you want to give it a station and offset, you would measure along this baseline to a point that is at a 90-degree angle to that point. So this is perpendicular offset to that point. And in this case, we've got a station of 2 plus 75, so we know that that intersection point from station 2 to that point is 75 feet. We know that from that intersection point out to that object is 125 feet, and that is right of the baseline, so that's going to have an offset of 125 feet right. So that object is going to have a station and offset of 2 plus 75, 125 feet right. As we come around the curve, and we'll talk a little bit more about how to handle curves, but as you can see, the curve, the stationing follows the curve around. So as we get to this point, this is perpendicular, and we'll take a look at this a little more in depth on the next slide. But again, this is 90 degrees to this line, which is going to be a radial line through the center of the curve, and it's 42.15 feet past station 5, and it's 91.33 feet left of the baseline. So it has a station of 5 plus 42.15, 91.33 feet left. And again, here you can see each of those stations is equal to 100 feet. The plus is just used as a placeholder. So we know that this point, being a perpendicular offset to that object, is 75 feet from station 2, because it has a station of 2 plus 75, and we know that the distance from that baseline out to that object is 125 feet, and it's right of the baseline, so it has a station of 2 plus 75 and an offset of 125 feet right. And here you can see this is measured, this is a 90-degree angle, 75 feet from station 2 and 125 feet out to the point. On a curve, the point where the station hits is measured radially from the center, or the radius point of this curve, out to that point. So it's at a 90-degree angle to this local tangent, but that's the point. It's got to be radial, so a distance or a point, imaginary line from this radius point or the center line of the curve through that 90-degree point out to this point gets you that station. So along the curve, we know that that is 42.15 feet, and the distance out is 91.33 feet, and because this is going up station, it's left of the baseline, so it's 91.33 feet left. This just shows you a sample page of an engineering plan for a new roadway and this happens to be the west entrance into Parkland College from Duncan Road. And it just shows you how stationing is used on street plans. You can see out here we have the center line of Duncan Road, and we have a station on it of 162 plus 00.02. And then at the point where the center line of this new road intersects that, we have a station on this new west entrance of 10 plus 00. So we have a station equation that says on the center line of Duncan Road, station 162 plus 00.02 is equal to station 10 plus 00 on the center line of this west entrance road. That just gives you the correlation between this stationing and this stationing, because this road is going to have unique stationing. You don't want to repeat the stationing on that's used on Duncan Road on this road, because that would lead to too much confusion. Then you can also see all the points along the road. They have got a point here at station 10 plus 75, and they give you the offset, tell you how far left of the baseline it is, and then tell you what the proposed elevation of that point is going to be. Same thing over here. This is in a curve, but you have a station, an offset, and an elevation for points along the edge of pavement on that. Points for inlets are going to have elevations, station and elevation, so that you can see the stationing is used for points that you can use to stake out this proposed improvement. Along the center line, you get the same thing. You've got even stations along that and elevations. So it just serves as the backbone of all the improvements. This is the profile view of that same area. You can see out here we've got the center line of Duncan Road, and then at the edge of pavement it tells you what that elevation is and the slope, and then what the elevation is at key points. The PVC, the PVI, and the PVT are points that we've seen similar in horizontal curves. This is the same type of point. This is the beginning of a vertical curve. So in other words, this little sag curve that goes through here to smooth out the transition between two tangent lines. You've got the point of vertical curvature, the point of vertical intersection, and the point of vertical tangency. And we'll talk more about vertical curves later in the semester. But it gives you that information, gives you the elevation, proposed elevation at each of those points, and what the station is at all of those points. Down here you can see the station at even 50-foot intervals, and the existing elevation and the proposed elevation for each of those points. So every 50 feet along that center line that correlates to that plan view that we saw just a minute ago, these are all the stations, and this gives you elevations at the key points along that proposed center line. This is a cross-section view. So this is a series of cross sections, and you can see again this is at station 12 on that proposed entrance. This is the center line of the roadway, and then this would be, as you're looking up station, you can see we're standing here, we're looking up at station 12 plus 50, station 12 or 13 plus 00. So all of this is going to be improvements that are right of the baseline. All of these are going to be improvements that are left of the baseline. So all of these would have right offsets, all of these would have left offsets, and this is going to be the baseline or the center line of the road. Also given is how much cut and fill is needed to meet these grades that are required. This shows a curve, and we'll talk about the stationing on the curve. This is where that entrance meets the perimeter road entrance out here on the west side of campus. We'll zoom in on this a little bit so you can see this curve and how it's handled a little better. So you can see as we come along on the stationing, the beginning point of the curve here is at, this is the PC of the curve, it's at 16 plus 27.90. And then you can see the stationing follows the curve around. Here's station 17, etc. So it doesn't follow the tangent necessarily, it's got to have the stationing following the curve. So if we take that station of the PC, 16 plus 27.90, and we add our length of curve, which in this case is 149.64. So if I come over here and I take 16 plus 27.90, which is my PC, and I add 149.64, which is my length, that's going to give me the station of my PT, or my ending point of my curve, and that's going to be station 17 plus 77.54, and that's our PT station, and you can see that that's where that number comes from then. So you follow the stationing, follows the curve around the arc, and so you use the L for that length to get to the PT. The one different thing is that we need to know what the station is on the PI, which is the intersection point of the two tangents. We need to determine that station so that we can lay it out. As we're laying out this tangent, we can lay that PI out in the field. And to get to that, we're going to take our PI, or PC, of 16 plus 27.90, that's our PC, and we're going to add our tangent length to that, because that tangent length is this distance from the PC to the PI. It's also the same distance from the PI to the PT, but we don't station around the tangent, we just station up to the PI. We station around the curve, but in order to be able to stake that PI out, we need to know the station on that. So we add our 76.41, which is our T distance, and that gives us our PI station of 17 plus 0.4.31. That's our PI, and you can see that that's what we've got down here. So that's how we determine the stations along the curve. Again, the curve stationing is going to follow along the curve and use the length of curve to determine where the PT is, and then the PI is just going to be used with the tangent length. Here you can see an overview of a subdivision with several side streets coming off of main lines, and as you can see, every street has its own unique stationing numbers. So the stationing on this street is 41, stationing down here is in the 30s, up in the 50s, and then at every intersection is going to be another station equation. So let's zoom in on that, and you can see here is the intersection of Sandstone Drive and Peppermill Lane. So the station along the center line of Peppermill Lane is 135 plus 91.39 is equal to the center line of Sandstone Drive, a station of 50 plus 00. So you can see each street has its own unique station, so that you don't have overlap and get confused with stations on Peppermill Lane and stations on Sandstone Drive. So you need to come up with a unique station number for each, or stationing system basically, for each side street that comes off of that. And the same thing down here, we can see that on Peppermill Lane we have a station of 133 plus 11.39 is equal to station 40 plus 00 on Rockdale Drive. So then the stations increase as we go around this way on Rockdale Drive. Stations increase as we go around this way on Sandstone Drive. We'll take a look at the other end of Sandstone, and you can see where it hits Bluegrass Lane, we have another station equation. So on Bluegrass Lane, the intersection of the two center lines is station 9 plus 38.88 on Bluegrass Lane is equal to 58 plus 80.00 on Sandstone Lane, Sandstone Drive. So you have another station equation at each point where one of these side streets ties into another point. You're going to have another station equation. This is from one of the practice problems. This is another type of station equation that you'll run into. This is where you're trying to get to match up with existing stationing. You'll see this type of equation where you've got a back and an ahead. So in that case, what this line is from A to B is going to be going from station 119 plus 47.36 to the back station of 128 plus 64.31. And then you're going to have an equation. So from this point forward, you're going to start at this point with 128 plus 77.49 and go up to this point of 143 plus 11.60. So from B to C is going to be this, using these two stations, this station and this station. And then from C to D, you're going to be using the ahead station of 139 plus 93.22 and 144 plus 77.26. So if you wanted to find the distance between A and B, you would take 128 plus 64.31 and you would subtract 119 plus 47.36. And I'm not going to do the math for you because this is one of your practice problems. That will get you A to B. B to C is going to be station 143 plus 11.60 minus 128 plus 77.49. And then from C to D, you're going to do 144 plus 75.26 minus 139 plus 93.22. And that'll give you the distance between those points. And then you could add all three of those up to find out what the distance is from A to D. And again, when you're subtracting that, if we want to do this, to enter it into your calculator, you're just going to do 143 11.60 because that plus is just a placeholder, minus 128 27.49, and that will give you the distance from B to C.